Yeah, start. Of course. Very good. Those are comments. Okay, so if there are no questions, let's begin with a recap of last day's uh, contents. Oh, there's a question. Okay, there's a question. All right. So, total postulate in quantum mechanics, will it increase or is it fixed? No, it is fixed. The postulates in quantum mechanics will not increase. So, yeah, now the thing is that the postulates you can just hold on a second, there's an echo somewhere. Yeah, so I'm unmuted here, right? Yes. Okay. So postulates, the thing is that you can write them, like you can divide them in different ways. So, but yes, the postulates are fixed, so they will not increase. Any other questions? Okay, if nothing else, then let's start with a recap of what we had done in the last tutorial session. So, if you remember that we looked at the Stern-Gerlach experiment and we explained the Stern-Gerlach experiment in terms of quantum mechanics. So, using the postulates of quantum mechanics that we had um, uh, which we had laid down previously. So we had seen that if you put a Stern-Gerlach apparatus along some direction, say n hat, and then put a screen in front of it, that is equivalent to measuring the component of the spin angular momentum along the n hat direction. And we also argued that even if you don't put the screen in the entire portion, so like this, even if you put it in the lower arm or the upper arm, even in that case, we are actually measuring SN hat and all the things which the postulates of quantum mechanics tells us that the measurement quantity will be one of the eigenvalues of the observable being this Hermitian operator, and after measurement it will collapse to one of the eigenvectors. So all those things will happen even if you put one screen over here. And we looked at a few cases. So we looked at the case where you first pass through a Stern-Gerlach along the z direction, and then so you got 50% in the down z, 50% in up z, and we blocked the down z and we put it into another Stern-Gerlach apparatus, and uh, at its output we saw only up z and no down z here. So, and we saw that this is because of the fact that the component of up z along down z in zero, or the projection along up z along the of up z along down z is zero in the complex vector space C2, which was our Hilbert space which we were working in. And if you also, we also looked at this case where instead of the Stern-Gerlach along Z, we put a Stern-Gerlach along the X direction. And in that case, we saw that 50% comes to up x and 50% comes to down x. And this we saw is because of the fact that the component of up z along up x is 1 by root 2, and also component of along up z along down x is 1 by root 2. They are the same. And mod squared of the component gives us the probabilities. That's why we have half of probabilities of going up or going down. Also, we could think of it in another way. So the upset state you can write as a linear combination of, so 1 by root 2 up x and plus 1 by root 2 down x. That is a linear combination of up x and down x. And this is something which is also called the quantum superposition. And so since we can say that since up z is in a quantum superposition of up x and down x, then when we will measure, we will get some probability. So half probability here of getting up x and half probability here of getting down x. Now, if we ask the question, okay, before we did the measurement along the x direction, was it in the state up x or was it in the step down x? So the answer to that question is that no, it was not in up x or down x, but since it is in a linear combination, we can kind of say that it is in both up x and down x at the same time. Now, this is the closest human interpretation that you can give to quantum superposition. And okay, some people might argue that okay, this is not probably um, possible that it is up x and down x at the same time. So we really don't know what is going on in the quantum states. We just have these postulates and we get probabilities and stuff, measurement statistics from the laws of quantum mechanics. The quantum mechanics doesn't really tell us what is really going on inside the system. Is it up x and down x at the same time, or is it something else which is going on? But the closest human interpretation is probabilities. Okay. And we also looked at the another case where we had the Stern-Gerlach along Z and again Stern-Gerlach along X, and after that we put another Stern-Gerlach along the Z direction. And there we saw that, okay, in the third screen, which we put here, uh, by classical intuition, we thought that we should see only upset, because you see here we have taken only the upset spins, and then again we are filtering the apex spins. So we would expect that whatever comes out of the Stern-Gerlach the final Stern-Gerlach apparatus will have this h cross by 2 component along plus h cross by 2 component along z and plus h cross by 2 component along x. So it should not have anything which is minus h cross by 2 component. But in quantum mechanically, we saw that, okay, out of the 50 that comes here, half of them go here, half of them go here. And that is also can be explained in a similar way by superposition, because apex can again be written as a superposition of up z and down z, and it is an equal superposition. So 1 by root 2 up z plus 1 by root 2 down z. And you can again take the projections and mod square to find the probability. This is what we learned in the last class. And so here we had worked with this SZ, SX, and SN operator. So today I'm also introducing the SY operator. And we can see that SZ we had written as this matrix. Now this 1, 0, 0, -1 matrix we are now writing as sigma Z. So this is called a Pauli matrix. So sigma Z, sigma X, sigma Y are Pauli matrices, these three matrices. And we saw that SZ has, we found out the eigenvalues and eigenvectors of all these matrices, and we saw that whatever be the direction, whether it is Z, X, or Y, or some random direction N, the eigenvalues are always plus h cross by 2 and minus h cross by 2, but the eigenvectors of these different operators are different. So for example, for SZ, it is just ket 0 and ket 1. For Sx, it is a superposition of 0 and 1. So one is a plus superposition, one is minus superposition. That's why we write as ket plus and ket minus. Similarly, for Sy, only you can see that in y here you have 0 plus I1 by root 2 and 0 minus I1 by root 2. So it is, so we denote it as ket plus but with a subscript I, and ket minus with a subscript I. And Sn, on the other hand, the general operator, which we saw, is so last day I didn't write this description or notation, but you can, so if you just form a vector with these three matrices like sigma x, sigma y, sigma z, so basically a vector operator sigma, then sigma x, x roof, sigma y, y roof, and sigma z, z, z roof. And if you try to find out the component along n, that will give you sigma n. So Sn is again just similarly h cross by 2 sigma n, where sigma n is defined like this, sigma dot n roof, where n roof is some unit vector in our real space, which is given by this. And we found up and get up and get down and so it was like this superposition cos theta by 2 e to the power I phi sin theta by 2. So here 0, here 1, and similarly down n. And for all of these cases, like for whatever direction, whatever this n be, we found out that the up n and down n are orthogonal to each other. So this is what we had learned so far. So any questions on that? Any questions on all these things which I said just now? Okay, so if not, let's move on to uh, our agenda for today. So basically one of our agenda for today. And so if you remember that we had discussed in some previous sessions that the set of all 2 by 2 complex matrices is a vector space on the field of complex numbers. And we had also calculated the one basis of this vector space, and that was the outer product of 0, 0, 0, 1, 1, 0, and 1, 1. And these outer products are basically nothing but matrices, which, so for example, 0, 0 outer product looks like this. Okay. So this is what we had seen. And so you can see, show that the Pauli matrices we just defined now, so sigma x, sigma y, sigma z, along with identity is also a basis for the same vector space. And also another notable thing is that in many books and papers or literature, you will find that sigma x is also just sigma x, sigma y, sigma z are just simply represented by capital X, capital Y, and capital Z. So these are the polymatrices. And you can try to what you can try to do is try to express n, which is a matrix given like this, in terms of these um, uh, in terms of these matrices. So in terms of these spaces, basically. Okay. So with that, let's go to our main agenda. So today we would like to learn about phases, the importance of phases in quantum mechanics. And so there's two types of phases can occur. One is the relative or local phase. One is the global phase. Okay. And now let's try to understand what these things are. So let's say let's take a state kit side. So take it like say C1 kit 0, C2 1. So basically, if you would write it as a matrix, it would basically a column vector, then it would look something like this, C1, C2. And so previously, I think in session 3, we had calculated that what is the probability of getting the different eigenvalues of Sz. For example, we found that plus h cross by 2. So this you can just read off from the this expression itself, because 0 and 1 are nothing but the up z and down z. So the projections, and if you calculate, then it will be the C1, and so probability is z plus h cross by 2 we've calculated to be mod C1 square. And probability that is z minus h cross by 2, we calculated. Okay, let me do something. Let's keep some space here. Yeah. So mod C1 squared, something like this, and mod C2 squared. Okay. And we also wrote down psi in the plus minus basis, that is in the basis of um, sigma h, and it was something like this. Note that ket plus and ket minus are nothing but up x and down x kets. Okay, so from here we also found that the probability of getting, say, Sx plus h squared to would be something like C1 plus C2 by root 2 whole squared, and probability of getting Sx minus h squared 2 is, okay, again, let's leave some space here. Okay, and here it would be C1 minus C2 by root 2 whole squared. Now, let's ask the following question. If I change my state to, so it's the same, almost same state as before, but I just add some phases. So let's add e to the power I, say, some phase 5 here, let's say, okay? And also to C2, we let's add some e to the power I5. So basically you can take out, you can take e to the power I5 common also, C1 0 and C2 1. So since we can take out e to the power I5 common, this we call is a global phase. Now, let's try to do the same things for this global phase. So let's just copy paste from here. Okay. So, for example, if we try to now calculate the probability that is Z plus h cross by 2, what will it be? So previously it was just a mod C1 squared. Now you have a phase e to the power I5 with it. So it would just be e to the power I5 mod C1 squared. And similarly, e to the power I5 mod C2 squared. And if we write it in this basis, it would be something like e to the power I5 C1, e to the power I5 C2, e to the power I5 C1, e to the power I5 C2. Or you can also take e to the power I5 common from this and write it like, say, e to the power I5 C1 plus C2, something like this, and e to the power I5 C1 minus C2 by root 2 into ket minus. So you can write it like this. And in that case, if you find out the probability of getting Sx plus h cross by 2, it would be e to the power I5 whole squared. And note that e to the power I5 C1 squared, okay, and here it would be e to the power I5 C1 minus C2. Now what is this? What is mod E5 C1? So mod e to the power I5 is 1, right? So basically, if you calculate this, then you will just get mod C1 squared. And again, mod e to the power I5 equal to 1, and then you would get here mod C2 squared. And similarly here, so mod C1 plus C2 by root 2 whole squared. So because this is 1, and here you would get C1 minus C2 by root 2 whole squared. Okay. Now, if you see that previously also the probability of getting Sz plus h cross by 2 was mod C1 squared. Now it is a mod C1 squared as well. Previously also it was mod C2 squared. Now it is the same. And even here, it was also, it's the same as before, like same as in this case. So these are all same. So basically, when I added the global phase, my measurement statistics did not change, which means that, so what do I mean by measurement statistics? So basically, let's say you prepared n copies of this state. So C10 plus C2. You prepared n copies, n identical copies. And like you prepared them initially. So in quantum mechanics, as we shall see later, that you cannot really copy any state. So you can generate one state and make photocopies of it. But if you prepare something under the same conditions, then the same state will be prepared. So let's say we have done that. We have prepared in identical copies. And what we are doing is we are measuring, say, S set. So how many of this we will get approximately in S set plus h cross by 2? We will get n into the probability. So mod C1 squared, let's say, and n into mod C2 squared. And similarly, n into this thing and n into this. Okay, so that is the measurement statistics. So if I measure n times, how many times am I getting sz plus h cross by 2 or sx plus h cross by 2? That is the measurement statistics. So my measurement statistics is not changing. So, and so all, and let's say, let's not write it as psi. Let's give it a different name, psi prime, let's say. Okay, psi prime. So all measurement statistics are exactly the same for psi, get psi, and get psi prime. Okay, and since they are the same, all measurement statistics are same, then you cannot really distinguish them apart. So basically, they represent the same physical state. Psi and psi prime are not different actually. So psi and psi prime are sorry, represent the same physical state. So in other words, like if psi prime is some global phase, say just in this case it was e to the power I phi psi, you can actually ignore the global phase. You can just write ki psi prime and psi are the same. Okay. So basically the conclusion here is that global phase, any global phase can be ignored. Or uh, equivalently, you can add any global phase. So you can just multiply any wave vector with e to the power I phi and still have the same state. And I remember that when we had been doing this unitary evolution, like the postulate of time evolution, somebody mentioned that, okay, so I asked, okay, what is something which will not change the norm of your vector? And somebody said, okay, if I add a phase, it won't change the norm. So yes, it does not change the norm, but it doesn't change the state also. Okay. So is this part clear to you guys? Any questions? So do you guys agree with me that global phase can be ignored? Anybody? Yes, no, anything? Okay, okay. So yeah, hopefully you guys have understood this part. Now let's come to the other counterpart. That is, now let's ask, okay, let's say I take a side double prime, and here I add a phase to on the first part, let's say, or let's say um, we add the phase only to the second part, let's say. So e to the power I5 C2 1. So previously, so psi was C10 plus C20. Now I have put a phase here. So this phase, so if you can see that this is a phase of for the KT1 with respect to KT0. So it's an additional phase which has been added, and so this is known as local phase or relative phase. Or simply, since global phase does not have no significance, generally we can also refer to as it as a additional phase. Okay, and if we do this now, let's again do the same thing for the. Okay, I think I had already copied, so I should be able to paste. Yeah, so let's do the same calculations again. Okay, so here this is the probability is set plus h cross by 2. Here it is c1 only, so it would be mod c1 squared as before. It would be e to the power I5 c2 because now this additional phase has come. And now as mod e5 is e to the power I5 is 1 as we had argued, this is again mod c2 squared. So it seems that, okay, even when the local phase is there, see previously also for psi, if you see, it was C1 squared and C2 squared, the probabilities. And even now, it is exactly the same, mod C1 squared and mod C2 squared. Okay, then let's now think about what happens to this. What happens to these probabilities? Do they also remain the same? If they remain the same, we can ignore it. Otherwise, we can't ignore it. So here what will become is that when you write this psi double prime in the basis of plus and minus, that is the basis of sigma sx, then you would find that here you would find instead of c2 e to the power I5 c2, and here e to the power I5 c2. So when you calculate the probability, it would be c1 plus e to the power I5 c2 and this thing, so mod c1 plus e to the power I5 c2 by root 2 whole squared and mod c1 minus e to the power I5 c2 by root 2 whole squared. And this is not equal to the probability that we had. So this is not equal to C1 plus C2 by root 2 whole square, which we had before. So you see that adding the relative phase apparently did not change the measurement statistics of S. But when we measure effects, the statistics change, the probabilities change. Okay, the probabilities of getting plus h cross by 2 and minus h cross by 2, they change. And therefore, we can say that, okay, although global phases can be ignored, local phases cannot be ignored. So till here are you guys with me? Do you agree with this? Any questions, doubts, anything? Okay. So, if this is clear, then let's move on to our next part. And let's try to ask ourselves the following question. That is this possible? Is it possible to have representation of complex vectors in real space? Is this at all possible? Like we have this space C2 and all our vectors are complex vectors of this form C1, C2, where C1, C2 are complex numbers. Now this vector do you think that we can be able to represent them? So obviously, since this is a vector in the complex space, it will be a vector in the complex space only. It will never be a vector in the real space. But can we represent this vector in the complex space? Any ideas? Any guesses? Like, feel free to make any wild guess. You can unmute or say in the chat any wild guess. Okay, uh, like, can we do this? Any guess? So I'll give you a couple of minutes to think if needed. That's not a problem. Okay, so Aman has made a guess. He has said ki 4 by 4 matrices. Uh, 4 by 4 matrices. Yeah, I understand what you are saying. You're saying ki, okay, the complex number C1 can be represented as, like, in terms of two real numbers, like x1 plus iy1. So x1, y1 are real numbers, or x2 plus iy2. So something of this form. So you can have a vector, you can form a vector x1, x2, y1, y2. And this vector would lie in the space R4, which is a real vector space. That is, it is a vector space on the field of real numbers. Okay. So yes, it is indeed possible to represent complex vectors in the real space, because R4 is a real vector space. But now let me ask, can you represent this complex vector in R3 or in R2? Can you do that? And by the way, you can also write this as in terms of, say, R1 e to the power I phi 1, sorry, phi 1, and R2 e to the power I phi 2. So again, you can write as R1, R2, phi 1, phi 2 belongs to R4. So you can always write this in a real space. So R4 is a real space. Now, can you reduce this representation to R3 or R2? Is that possible? So again, I'll give you some time to think about that. So what you were saying, that it would be not really 4 by 4 matrix, but if you want to represent it in matrix form, it would be some 4 by 1 matrix actually. Yeah, I understand what you were trying to say. So yeah, you're right. Okay, four real numbers can be used to express two complex numbers. So now I would like you guys to think about this, whether you can reduce this complex number to something in R3 or R. We can reduce to R3 by normalization condition. Yeah, very good. So what Aman again is saying is that since norm of psi is 1, as we have said, okay, norm square gives us the total probability, and since that should be 1, norm should be 1, and all the state vectors are unit vectors, like I have probably repeated a million times by now. So, so if you find the norm of this, then you will have a constraint, okay, r1 squared plus r2 squared. So I'm taking this polar form and not this Cartesian form. So r1 square plus r2 square should be 1. Yes, that is a constraint. And since this will be the case, you can, of course, do the following. You can write r2 as root over of 1 minus r1 squared. So basically, psi you can now write as r1 e to the power I phi 1 and root over of 1 minus r1 squared e to the power I phi 2. Okay. So now we have three like real numbers r1, phi 1, phi 2, and this is indeed a member of R. Now I want to go further. So can you think of a way to reduce this further to R2? And the spoiler alert is that there is a way. So can you think of a way to reduce this to R2? So think of what we just learned right now. Think about physics. So that's another thing. Yes, exactly. So as we had said, the global phase, we can always ignore a global phase. So what we can say, do is we can take, say, e to the power I phi 1 account. Okay, that would give us R1, 1 minus R1 squared. And here, this would be I phi 2 minus. And we have said that we can ignore this global phase. So just ignore. So we'll just rub it off. So, okay, maybe I'll not rub it off so that you can understand later on. So I'll just write that this is equal to, you can just ignore this phase and write this. And let's say phi 2 minus phi 1 is delta phi. Okay, so now we have reduced it to two real numbers, R1 and delta. So if we have this R1 delta phi, and this is a member of R2. So for every psi uh, belonging to C2, so by the way, this opposite E, like horizontally inverted E, this means for every. Okay, for every psi belongs to psi 2, we can find a tuple in the real space like R1 delta. Okay, now you notice that R1 and root over of 1 minus R1 squared both have to be real numbers. So R1 has to be between 0 and 1. And delta phi is just an angle. So because say e to the power I delta phi, and it will start repeating after say 2 pi. So delta phi would be somewhere in 0 to pi. Okay. So we can form a real space, like a real in the real space we can represent for every psi. So within this box, so basically from 0 to 1 and 0 to 2 pi, within this box, all the states, all the size can be represented. So for example, some psi might, this point might correspond to some psi, this point might correspond to some psi. Okay. So yeah, you can actually represent. So basically, this is a representation of C2 in R2. So we have our real representation. But the problem is that it's not very, this representation that we have found here is not very uh, intuitive. Okay, in the sense that if I say join from the origin to this vector, they would have different lengths. But in C2, the vectors were all unit vectors. So when I'm representing in R2 like this, the lengths are changing. So I do not have that basically in my mapping from this C2 to R2, the length of my vectors change, which is something which I really don't want. Okay, so here we had represented in a plane, sort of like we had represented C2 in a plane. So plane is a two-dimensional object. So what other two-dimensional object you can think of where we can represent this? And I want such a, so actually it's, don't think of, so, okay, by two-dimensional object, I should clarify that, okay, so you can, if you, even if you bend the plane, it's still, yeah, surface of a sphere, right? So surface of a sphere is a two-dimensional object. So uh, here we have found out, okay, we can represent C2 by two real numbers. Here we have chosen R1 and delta. But we need not choose R1 and delta, right? We would choose something else. In fact, unknowingly, we have already done this. I'll show you where. Like the eigenvector of Sn here. So here you see we represented by we used just two real parameters, theta here and phi here. Okay, so let's try to see. Let's try to take this and let's try to see how we can represent it on a surface of a sphere. Okay, so now we have this theta. So instead of R1 and delta phi, instead of this, we are now taking two other real numbers, theta and phi, which are again in R2. Okay. And so basically in the column matrix form, it will be cos theta by 2 e to the power I phi sin theta by 2. And also notice that if you again take the norm of this, then cos squared theta by 2 sin squared theta by 2 will be 1. So if you add cos squared theta by 2 and sin squared theta by 2, you get 1. So the norm is again 1. Okay. And there's no, we have already taken out the global phase. So only there's a relative phase sitting here. Okay. Now, if we use this theta and phi, and then we can represent our this vectors in the like in on the surface of a sphere. So some sphere like this, let's say. My drawing is bad, so forgive my drawing. So the dotted circle which I am drawing is the XY plane, and basically the cross section, this cross section circle in the XY plane, and the solid line is a cross section circle in the YZ plane. So let me mark the axis also. X, Y, Z. Okay, and So if I have this, so let's not write it as up n, let's make it psi. So if I have a ket psi, which looks like this, cos theta by 2 e to the power I phi sin theta by 2, okay? Then we can represent it uniquely by a point on this, on the surface of this sphere. So in such a way that this is theta, and the, if you take the projection, say in the xy plane, then that makes an angle phi with the x-axis. Is this part clear to all of you? Any problems? So basically, the surface of the sphere was also a two-dimensional object, so to speak. Like it lies in the 3D space. Like if you take the volume of the sphere, for example, that is a three-dimensional object. That has to be a three-dimensional object. But in some sense, a sphere, you can just think of it as basically, if you're just walking on the surface of the sphere, then you can basically map out the whole thing using only two real numbers, which is theta and phi. Is that clear to you guys? Any questions? Yes, yes, exactly, exactly. It is exactly the same concept like stereographic projection in complex science. Exactly, yes. It is very similar concept. Only, okay, there is I think a little bit of difference in the sense that uh, yeah, like there the space was only complex numbers. Like it was not C2. You had only one complex number, C. And then basically the Argand plane you project stereographically projected onto a sphere. Right. So yeah, it's similar. The concept is very similar. Yes, that is right. Okay, so any other questions? So is this clear that we can, so corresponding to every side, there will be a point on the surface of a sphere, and I will define, since I need only theta phi, I can define the radius to be 1. And if I do that, then, and if I take the center of the sphere to be origin, then the length of my vector is also 1. So that correspondence is also maintained. See, in C2, my norm psi was 1. And let's say we have a vector, some vector here, v vector, okay, which corresponding to psi, we have a vector v vector here. And the length of that vector is also, okay, so that correspondence also here. So now, just like we had said, so we can say that for every kit psi in C2, we can actually find a vector, v vector, which can be uh, written down in the polar coordinates, for example, as something like sin theta cos phi x roof plus sin theta sin phi y roof plus cos theta z roof. Okay, so there exists for every side there is this vector v vector, which is in R3 and which represents ket psi. And this vector representation in the real space is known as the block vector. And This sphere, this sphere of unit radius is known as the block sphere. Is this okay with you guys? Okay. So if there are no questions, now let's try to locate the different vectors that we know on this block sphere. So let's say, so let me draw the block sphere again. And these are the axes, Z, Y, and X. Now I'm asking, how can I represent this upset or K0? And remember, K0 is nothing but 1, 0. Okay, so how can I represent this? Now, also, let me write this again. This is the general form that it will take, copy, and let me just keep it here, this form. Uh, okay, what? Sorry, I copied the wrong thing. Copy, and there you go. So basically, you have to find theta and phi so that this thing here becomes 1, 0. So can you tell me what theta and phi we have to use? So basically, you have to choose theta and phi in such a way that this becomes 1 and 0. So cos theta by 2 has to be 1 and e to the power I phi sin theta by 2 has to be 0. Theta equal to 0, right? And phi can be actually anything because so if you take theta equal to 0, the only point that you will get is this point. Because what is theta? Remember, theta is the angle with the z-axis. If the angle with the z-axis is 0 and it is a, like if you're looking at the surface of the sphere, this then only this will be and phi will sort of, so you can assign any value to phi, it doesn't matter because what was phi? Phi was the projection of this like the projection of the vector along the xy plane, and what does that projection, what angle does that projection makes with the x-axis, that is phi. But now along the xy plane there is no projection because it is along the z direction. So phi can be anything. Literally, phi can be anything. It doesn't make a difference what value of phi you choose. Okay. But okay, let's, for just the sake of simplicity, let's put phi equal to 0. So yes, so this is the point on the block sphere which corresponds to ket 0 or upset. Now, let's take this down z or ket 1, and this is 0, 1. Okay. So now can you tell me what value of theta and phi we have to choose? So here you have to choose theta such that cos theta by 2 is 0 and sin e to the power I phi sin theta by 2 is 1. Okay, so yes, you are right. Theta has to be 180 degree. So, or rather, I would write in radians. Theta has to be pi radians. So, because if theta is pi, then the cos pi by 2 will be 0 and sin pi by 2 will be 1. But what about phi? What should be the value of phi? Yeah, it is in general 2n pi. That is true. But let's say, so it's actually, let's restrict ourselves, let's restrict the values of phi to say um, only say minus pi to plus pi. Okay. Or shall we do that? Or let me think. Theta, or okay, let's restrict it to 0 to 2 pi. And let's restrict the values of theta to uh, closed here and there. And let's restrict the values of theta to say 0 to pi. Okay. If we do this, then 2n pi in general will become 0, right? Because yeah, you can take 2n pi, but then it will be just cyclic. Okay. So if we just take this restriction, then like they won't mean anything physically different. For example, 2 pi and 4 pi will lead you to the same point. So let's take phi equal to 0 for that. So just by putting n equal to 0 in 2n pi. Okay. So theta is pi and phi is 0. So that you can see. So theta is pi means it should make an angle of 180 degree with the z axis. And phi is 0. That means there will be basically, that means it would be either along the x-axis, but since theta equal to pi means that it has to be along here, and the component along x-axis is 0, so phi equal to 0 condition is also met. So this corresponds to k. Is that okay? Any confusion regarding this? Okay, like do you mean it is not clear or there is no confusion? It's clear. Okay. Okay. So now just for the heck of it, let's do it for um, this our up x and down x as well. So let me draw the block sphere again. Okay, I'm probably getting better at drawing the circles, I guess. Uh, and the axis here, y. Now we let's take up x and down x, which are the eigenvectors of Sx, and this, if you just write in the matrix form, is like this. Okay. And again, we will just paste that general form here, and we will ask the same question again. Okay. Let's try to find corresponding to apex or ket plus and ket minus. What are the points on the block scheme? Where can I find the previous tutorial recordings? Yeah, you can find them on YouTube. So for tutorials 1, 2, 4, there the whole recording is there on YouTube. I think I'm not sure if tutorial 3 is there in YouTube because we had some technical difficulties and we had to record it offline. Like as in we were not live on YouTube. I don't know if that has been uploaded later on. That is, the recording is there, but I have to check if that has been. So yes, you can find the tutorial recordings on YouTube. Okay. And I think for tutorial 3, even the first half an hour which is there on YouTube, that there was some kind of noise. So if possible, later on I will try to uh, basically shoot that again offline. So basically record that offline and then upload the whole thing so that you can refer to it as and when required. Okay. So now back to the question. Okay, what values of theta and phi you would take in order to get, say, apex? Okay. So basically, what point corresponds to apex here? For plus, theta is pi by 2 and phi is 0. So uh, that theta pi by 2 phi is 0. So let's see if that does it. So theta pi by 2 if you take, then cos pi by 4 is 1 by root 2. Okay, sin pi by 4 is 1 by root 2. And phi is 0, so e to the power I phi is 1. So 1 by root 2, 1 by root 2. That's right, yeah. So theta is pi by 2. That means the angle with the z-axis is 90 degrees. So it is somewhere in the xy plane. And phi is 0, that means the angle with x-axis is 0. So it's basically along the x-axis. So this point is apex or get plus. Okay. And for minus, you said, okay, so this is for plus x, and for minus is write in polar coordinates. Huh? You take theta in 0 to pi and phi 0 to 2 pi. So yes, theta 2 pi minus pi by 2, uh, or you can just take, say, theta, let's say, uh, what can you take? Well, 2 pi minus pi by 2. By the way, why do you need 2 pi minus pi by 2 and phi 0? Okay, you can do that. Or you can do that theta is, you can take pi by 2 again, and phi, you can take pi. Because e to the power I pi will be minus 1. See, this will give the minus 1. And theta pi by 2 will give this. Okay, and okay, so I understand. So Anmol's answer was, ki, instead of this, can you write theta 2 pi minus pi by 2 and phi 0? Okay. So 2 pi minus pi by 2, which basically means, I think, 3 pi by 4. Okay. And phi 0. But okay. Uh, so let's see. Yeah. So cos 3 pi by. Oh, I'm sorry. What I meant to 4 pi by 2, 3 pi by 2. I'm sorry. Yeah. So let's say if this also makes it, then you can put cos 3 pi by 4, and that will be minus 1 by root 2. Here it will be 1 by root 2, and you can take phi 0, so you can take minus common out. And this will again give you, okay, let's see. Uh, there is probably some problem with this. Let me try to think. Because corresponding to one state, there should be on uniquely one point. 2 pi, but is it outside the range? Because theta is 0 to 2 pi. Oh no, okay, theta is 0 to pi, right? Yes, it is outside the range. So yeah, right, exactly. So theta has to be within 0 to pi, so it has to be outside, inside this range. And if you do that, then you will find. Okay. Yeah, I also got confused. I'm sorry. Yeah. So theta pi by 2, now phi is pi. So again, theta pi by 2 means it's in the xy plane, and it is making an angle 180 degree with the positive x-axis. So which means that it is along the negative x-axis on the surface of the sphere. So it's just 1 point. So down x here. Okay, nice. Okay, right. So we have also found up x and down. And if you notice that all these so up x and down x are eigenvalues, eigenvectors, I'm sorry, eigenvectors of Sx. And if you notice that the eigenvectors of Sx are along the x-axis, the eigenvectors of Sz, which are up z and down z, this is down z, they are along the z-axis. And similarly, you can guess that if you have, say, some Sn, then its eigenvectors will be along the in roof axis. Okay, so basically, if you have this, then if you have this direction in roof, if this is the direction, and the eigenvectors of n roof are, say, up n will be along this, and along minus n roof axis, you will have some down n. So in general, you will have this. So you can see there is a beautiful correspondence that comes along. That when you express the vectors in C2 in R3 on the surface of the block sphere, um, then what you get is that the eigenvectors of the corresponding direction, in the block sphere, the block vector lies in that direction. For example, if you're looking at the eigenvectors of Sn hat, then the block vectors corresponding to the eigenvectors up n and down n, so these block vectors lie along n. Is this part clear to you guys? Okay, so maybe just for the clarity, let me write it because this is important. K block vector corresponding block vectors corresponding to up and down n lie along plus n roof and minus n roof respectively. Okay, so okay, all right. And one important thing which I would like to stress on is that, okay, I am writing Kate Apen, but it is actually what I mean is the block vector corresponding to Kate 1n. And when I am writing Kate down in here, when I am describing on the block sphere, this is the block vector corresponding to Kate down n. Okay, so it's just the representation of the vector. Okay, all right. So now let's maybe look at another interesting thing. That is, you can also notice that this up z and down z, they are orthogonal. Like in C2, they are orthogonal, right? Again, up x, down x are orthogonal. And so they are also here diametrically opposite. And here also up x, down x are orthogonal and in the C2 space. And in the block sphere representation, they lie on diametrically opposite points on the block. And similar for up and down. So actually, you can see that all the diametrically opposite points and in the literature, it's often referred to as antipodal points as well, the diametrically opposite points. So antipodal points on the block sphere represent points, represent states which are orthogonal. Sorry. Okay. So this is also a very important thing that we have to remember, that the correspondence is not everywhere. So we created a representation of C2 in R3, and we preserved some properties. For example, even there the norm was one, here the length was one. But here when they're orthogonal, you have to remember that the vectors are not at 90 degrees to each other. In fact, they are at 180 degree to each other. And that sort of comes from this theta by 2 here. So, so I'll end this section with a question for you to ponder about. Maybe we can discuss it in the next class. What if my general state, if I write it as just cos theta and sine theta to the power I phi, and we do not use this theta by 2. Okay, what will happen? So this is something that you can think about, and this we will discuss in the next class. Okay, now, um, okay, so let's move on to the next topic for today, and which is unitary operations on a loop. So, if you remember the last postulate that we discussed, that is a unitary postulate, then that's told us okay, if there is a quantum system and if you have a state in that system, and uh, the state will evolve in an unitary fashion, like the evolution of the state will be given by a unit, in the sense that if you have say psi 0 and you want to find psi t, then it would be some unitary acting on psi 0 will give you psi t. So this is what the fourth postulate, the unitary evolution or the time evolution postulate of quantum mechanics told us. Now we also, at the time, we also learned that if how can we find u? Can find u from some this Schrodinger equation. So there will be some Hamiltonian which will lead to this q. Now, in this series of sessions or in the tutorial sessions, we will not really worry about what Hamiltonian causes the. So I will tell you this much, that for solid state systems, for example, say electron spin, nuclear spin, superconducting qubits, things like that. This H is actually uh, the time we we engineer a time dependent Hamiltonian in H. And when we give this time dependent Hamiltonian, then for a certain period of time, let's say, then we get this unity. And this time dependent Hamiltonian can be engineered by giving a pulse of electromagnetic radiation. And if you want to understand, really understand how giving a pulse of electromagnetic radiation can perform unitaries or can perform a time evolution, then you really have to understand something called semi-classical light matter interaction. So semi-classical in the sense that matter or the basically the solid state system is considered to be a quantum system, for example, a qubit, but the light is considered to be a classical object. So it is not quantized. So if you understand this and specifically the concept of Rabi oscillations, then you would be able to understand how unitaries are actually given in time-dependent systems. And if you want to learn more about this, then you can look at the book Introductory Quantum Optics by Terry. And yeah, in a lot of other textbooks also you'll find this. Specifically, I think chapter 4 deals with this kinds of phenomena. So you can look at this, but here for our purposes, what we will assume is that there's some Hamiltonian, maybe it is a time-dependent Hamiltonian, maybe it is something else, which is leading to some unitary evolution. We will not worry about what Hamiltonian, what system is in, what Hamiltonian is there, because of which the unitary comes. Okay. And uh, yeah, and another important thing is that for say optics, for example, then the unitaries can also be um, uh, performed by some components like say half wavelet, quarter wavelet, etc. Okay. So we will not worry about what is the physical system. We will leave it to the experimentalist and uh, engineers to figure that out. How will they will perform this unitary? What Hamiltonian they will use, or what components they will use in this set? That we will not bother. So we will just take unitaries. We will say, okay, this is some unitary. So this can be obtained by time evolution of a quantum system, and so this is possible. We don't care which Hamiltonian is giving us the unit. And the unitary operations are lead to what in quantum computing they lead to what we call gates, or rather quantum gates. Okay, so when I'm saying a quantum gate, it is nothing but a unitary operation, which is there's an underlying system, there's some Hamiltonian, some component, something which does that, but we don't care. We just know that okay, there's some unitary operation which is getting uh, implemented somehow. Okay, so now let's try to look at some of the important quantum gates or some important unitary operations that we will face very frequently in quantum computation. So let's say the sigma x, the poly x matrix. Okay, 0, 1, 1, 0. So this you can check is a unitary. So let me show you that. So 0, 1, 1, 0, 0, 1, 1, 0. So this first row, first column, that will give you 1. First row, second column will give you 0 into 1, 0, 0. This will give you 0 and this will give you 1. So, okay, I'll rather let me write it as sigma x dagger, because that's what we have to check. And here the sigma x dagger is nothing but sigma x. So this is actually equal to sigma x squared. And you can see that this is adding. Okay. So sigma x is, so this is a unit and this is a quantum gate. Let's try to see how so if we look at the block sphere representation of the quantum states, how it affects different quantum states. Let's try to check that. So let's say you have a ket 0 and you operate the unitary sigma x on it. So what happens? Let's try to see. So sigma x is 0, 1, 1, 0, and this is 1, 0. So if you multiply this with this, then 0 into 1 plus 1 into 0, this will be 0. And then 1 into 1 plus 0 into 0, that will be 1. So this will give you ket 1. All right. And sigma x, similarly, you can find out acting on 1 will give you 0. So let's try to see on the block sphere what this does, what this means. Let's say this is our bat sphere. Let's say this is our block sphere. Let's draw the axis. Okay, so we looked at it a while ago. So can you tell me where the ket 0 and ket 1 lie on the block sphere? We did it just now. So ket 0 is on top, that's true, and ket 1 is on the bottom. Okay, since they're orthogonal, they have to be diametrically opposite or antipodal points. So 0 and 1 are like this. So we see that when we start with 0 and we apply sigma x on it, we actually go to 1. And when we start with 1, we go to 0. Right. Now let's try to see. So this is what it does on 0 and 1, for example. Now let's try to see what it will do to, say, the eigenvectors of Sx, that is plus ket plus and ket minus. Okay. So let's see what it does to sigma x plus. So this would be like this, and 1 by root 2, 1 by root 2. So what will I get? So this times this will give me again 1 by root, times this will give me again 1 by root 2. So it will give me back the same thing. Okay. So, and again, if you look at sigma x minus 0, 1, 0, 1 by root 2 minus 1 by root 2, then you will find that this times this will give you minus 1 by root 2, 1 by root. Now, again, we know that we can take a global phase out without changing the state. So we can write it as this. So, and this global phase can be ignored. So this is just ket max. All right. So when we start with sigma x, sorry, when we start with the eigenvectors of sigma x, so basically ket plus lies here. If you refer back to your notes, then we had calculated just a while ago, and ket minus is here. So we may start with the eigenvectors of sigma x, Sx, also the eigenvectors of sigma x, and we apply the unitary sigma x on it, then the states do not change. They just stay there. Okay. All right. Now, so we saw that what sigma x does, it takes 0 to 1, 1 to 0. It does not change ket plus, it does not change ket minus. Okay, this is what we have seen. And in general, if you apply sigma x on some general state, for example, cos theta by 2, 0, plus e to the power I phi sin theta by 2, 1, then what you will get is just, since this is a linear operator, and this is a property of the linear operator that you can just take sigma x inside, So sigma x 0 plus e to the power I phi sine theta by 2. Sigma x acting on 1. No, sigma x acting on 0. We can say that this we have calculated that sigma x acting on 0 is 1. So we can just put 1 here, and sigma x acting on 1, we have found that that is get 0. So let's just do that. Okay. Now, this is what the sigma x operator does. Now, from the fact that it does not change plus, get minus sigma x, but it flips 0 and 1, that is, it takes 0 to 1 and 1 to 0. Can you predict what kind of rotation of the block vector sigma x is causing? Can you guess? So if you take some general vector psi, so this will also have a block vector representation. So it will be some point on the block sphere, and sigma x will take it to some other point, which will be denoted by this 180-degree rotation about x-axis. Yes, that is true. But that is exactly right. And since it is about the x-axis, you can see that the points which lie on the x-axis, that is get plus and get minus, rather the block vectors corresponding to get plus and get minus, they do not change. Since it is a rotation about x-axis. And 0 is brought to 1, 1 to 0, so it's clearly a rotation by pi. So basically, sigma x rotates the or let me write it this way. Okay, applying the unitary sigma x on psi rotates the corresponding block vector about x-axis by 180. And you can also see it, if you're not convinced, you can try to write this equation, that is cos theta by 2 1 plus e to the power I phi sin theta by 2 0, in a form like this: cos theta by 2 0 e to the power I phi sin theta by 2 1. So let's try to do that. So let's take e to the power I phi common out. Then what we will be left with is sin theta by 2 0 here, plus e to the power minus I phi, because we've taken e to the power I phi common, so e to the power minus I phi will come here, and cos theta by 2 1. Okay. Now, of course, this global phase you can just ignore, and sine theta by 2 we can write as cos 90-degree minus theta by 2, or pi by 2 minus theta by 2, and e to the power minus I phi here, and this is sine pi by 2 minus theta by 2. So pi minus theta by 2 0 e to the power I minus phi, and sine pi minus theta by 2. So remember that this point, this vector cos theta by 2 0 e to the power I phi sin theta by 2 1, corresponded to theta phi on the theta phi on the block sphere. So what angles will this correspond to? Because see, they are the same form. Here instead of theta, you have pi minus theta. Here instead of phi, you have minus phi. So this will correspond to the point pi minus theta minus phi. And I'll leave you to visualize and convince yourself. This is actually a rotation of the block vector about x-axis by 180. Okay. So any questions, confusions on this? So is this clear what we have done here? That the unitary sigma is corresponded to some. Okay. Would you please explain physically what it is like? Sphere. Uh, physically, if I have to explain, uh, Rajrupa, can you unmute and please say ki what exactly you are looking for? Like, or you can also like, oh, okay, that's fine. Okay, so I'll try to explain. So, okay, how do I explain this? So, do you understand that this is a block sphere is just a representation of the complex vector in the real space? Do you agree with that? Yes. Okay. So that's the fundamental motive of the block sphere. Now, physical significance, if you ask, then one I would say I don't know if I call it a significance, but rather a correspondence is that the eigenvectors of the spin operators corresponding to some specific direction. So if you're measuring sigma x, say sigma z, sorry, sz, for example, if you're measuring this, then the physical significance is that the uh, that after you do the measurement, you would either find the state in ket 0 or ket 1, which is along the z-axis. So that is more of a physical correspondence. Um, does that make a little bit of sense? So it turns out that when you represent the complex vectors like this physical correspondence comes up. And in general, for let's say for Sn. Okay, so I would try to make this kind of clear. It's just a coincidence. And as you will see, like it's a coincidence that we get this physical correspondence out of this representation, but it is not always the case. For example, for C2, you can represent it in the real space, in a 3D space, for example. You can have a visualization. So, and if you are asking, okay, so block sphere, what can it help us for? Well, it can help us for visualization because see in C2 it's very difficult to visualize complex vectors, right? So if you have some tool in the real space and preferably in the 3D space, which can help you visualize the complex vectors, then that will be useful. And that's what block sphere is for. Okay. So is that kind of clear? Okay, okay. Then let's So for example, let's say sigma x, what sigma x was doing just by looking at this equation, we really can't say much. Like it's acting on a complex vector, it making the zeros ones and ones zeros. Like it doesn't make much sense. But when you look at the block sphere, okay, it corresponds to something like you can visualize it. You say that okay, sigma x is actually rotating the block vector around the x-axis by some angle. So in this case, 180 degree, for example. Okay. All right. So let's then look at some more examples of. So of course, sigma x, we saw that sigma x rotates block vector around, sorry, about the x-axis by 180 degree or by pi radians. And similar thing you can say for sigma y and sigma z. So basically, if you look at sigma y, for example, then and you can actually do the calculations and check that this will rotate the block vector about y-axis by pi, and similarly for sigma z. And in general, if there is a sigma n, where sigma n I had defined like that, sigma dot n. So if you take this, so this will also be a unitary, and this will rotate, as you might have guessed, about the n hat direction by pi. Okay, so basically, so sigma n rotates the block vector about the n hat axis. All right. Now, okay, so these are some of the. But there's another question. Okay? Block sphere is the standard or any other visualization available? For a single qubit, yeah, block sphere is a standard. To the best of my knowledge, there is no other intuitive visualization tools available. And in fact, it's block sphere, like it's available only for qubit, mind you. Even if you take say 2 qubits, then you can have a block sphere in. Or if you take a qubit grid, for example, where there are 3 levels, like here we have only gate 0, gate 1. If you have gate 0, gate 1, gate 2, then it will be vector in the Hilbert space C3. Okay, and in C for C3, you do not have a visualization in the real space, or there is actually no visualization tool available. So only in C2 do you have some visualization tool available, which is this block sphere. All right. Okay. So uh, let's look at another very important unitary, which is the Hadamard. And the Hadamard gate unitary looks something like this. This is called the Hadamard gate. Yeah, and also remember that all the unitaries that we are doing today are actually quantum gates. We'll use those quantum gates in the quantum circuits that we will be constructing later on. Okay, so let's try to see what is the Hadamard will do if it acts on say gates. Okay. So 1 minus 1 and 1 0. All right. So here you'll get 1 by root 2, and here also you'll get 1 by root. So if you write in the 0 1 basis, so it'll be 1 by root 2 0 plus 1 by root 2 1. And can you tell me what this is? What is 1 by root 2 0 plus 1 by root 2 1? We have the hint is that we have encountered this a lot of times till now. It is a superposition, but if I have to write it inside a kit, so what were we denoting this 1 by root 2 0 plus 1 by root 2 1? Right? Plus kit, right? Or so basically, this is eigenvector of sigma x. Okay, so this is something. These small things are some things which are like as you go on deeper into quantum information theory, so it would be very useful if you can remember the small things. And if you had minus here, you would have get minus. Okay. So let's now see how Hadamard what Hadamard get does on acting on ket one. Okay. So 1 by root 2 1 1 1 minus 1 0 1. So the first row with first column will give you 1 by root 2, but the second row with first column will give you minus 1 by root 2. So again, this would be 1 by root 2 get 0 minus 1 by root 2 get 1, and this would be get minus. Okay. So now again, let us try to look at the block sphere representation. Okay, what happens on the block sphere? Let's say so when we are starting with say ket 0. So ket 0 is here. Then we are ending up at ket plus. So ket plus is here. Okay. So we are going from here to here, from ket 0 to ket plus when we are applying the head. On the other hand, when we start from, let's say, ket 1, which is here, then we end up at, okay, let me draw this circle. This would be useful. Yeah. So we end up, so on applying the Hadamard on ket 1, we end up at ket minus. Ket minus is here. Okay. So can you guess what is the rotation which is taking place here? Actually, it's a bit non-trivial, so to speak. So maybe I'll just give you the answer. So it's basically rotation by angle pi or 180 degree about the axis x roof plus z roof by root 2. So let's try to justify this. Okay, so x roof plus z roof by root 2 will be in the xz plane. So some point like this. Okay, some axis like this. So this is x roof plus z roof by root 2. And we are claiming that all that it is doing is rotating the vector by 180 degree about around this. Okay, or about this. So one thing we know that if there's a rotation by 180 degree, it can be represented by some sigma n, where n would be something. And I am claiming that n is x rho plus z rho by root 2. So if I calculate like sigma n, where n is x rho plus z rho by root 2, I should get the head. So let's see whether we are getting that. So what we have to calculate is sigma x roof plus z roof by rho. Okay. And yeah, what is so before we do that, let's write down sigma n once again. So sigma n is cos theta minus cos theta e to the power minus I phi sin theta e to the power I phi sin theta like this. And I want to calculate now x roof plus sec roof by rho. So I have to find out what will be the theta and phi, right? So theta, if you see, theta is pi by 4, okay? And phi, since this is x roof plus z roof by root 2, you can see that if you take a projection on the xy plane, it will be along the x direction. And so phi will be 0. So we will get cos pi by 4 and e to the power I phi, phi 0, so 1 sine pi by 4. Again, this is 1, so sine pi by 4 and minus cos pi by 4. And both sine pi by 4 or sine 45 degree and cos 45 degree are both 1 by root 2. So we get this. And this is equal to the Hadamard gate. So because see we have defined the Hadamard gate like this 1 by root 2 1 1 1 minus 1. So sigma x root plus z root by root 2 gives us the same gate. Okay. So basically this justifies that. So we know that sigma n, if we have a unitary sigma n, then that will rotate the block vector about n hat axis by pi. So since we have sigma Hadamard is sigma x rho plus z rho by root 2, then it is rotating the by angle pi about x rho plus z rho by root 2. So that is the justification. Now, okay, today we are almost out of time. So next day we will try to see what about rotations by angles other than pi. Okay. So suppose I want to rotate by pi by 2 or some arbitrary angle theta, then how can I construct the corresponding unit? So today what we have learned is if I want to rotate by pi about some axis, then I have to use something like sigma n. And around x root plus z root by root 2, that gives me the Hadamard. So I'll so since we do not have much time right now, so I'll just end here today and I'll be here for some time if you have some questions or queries. And also tomorrow we will try to see what happens if we take this state, like cos instead of cos theta by 2, if we take cos theta and sine theta, what will happen? That so No, only cos. Okay, so there's a question. Only cos and sine is used in quantum. No tan. Uh, okay, that's a good question. Ki why only cos and sine? Well, no, it's not like tangent function is nowhere used in quantum mechanics. It's just that in our particular case, and in fact, if you just take like cos common out from here, you will just get tan. Yeah, exactly, exactly. Yes, yes, yes. But the thing is, yeah, so it depends on the problem that you are dealing with. So we are dealing with a very specific problem of a qubit, and here, say, uh, cosines and sines arise in our treatments. So global phase does not change angle. No, 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 no. So basically, let me just with the help of an example. So let's say this was case 0, right? Now I have added some phase e to the power I theta case 0, let's say. Okay. So e to the power I theta case 0 will be represented by the exact same point on the block sphere. So this is also e to the power I theta case 0 for any theta. So yes, yeah, that's why you know, yeah, that's a good point because when you give a global phase, the point on the block sphere does not move at all. Yes, that's right. Yeah, that's a good point actually. Yes. Is Hadamard matrices is represented in sigma z eigenvectors. Can you explain what you mean by that? Maybe you can unmute and yeah. Yes, yeah. Oh, okay. I understand. I understand. Yes. So when we are writing this, we are using the sigma z basis. That's correct, actually. So 1 minus 1. So basically, this corresponds to ket 0, ket 1, ket 0, ket 1. Okay. So basically, it's in the sigma z basis. Yeah. That is true. That is true. Yes. So Anmol is saying that we need to encode amplitude and phase of a wave function for simpler calculation. So we took psi to be an element of complex input space. That is why sine and cosine come naturally in notation matrices. Is that correct? Uh, yes, you can think of it like that. Um, Yeah, you can say that. I mean, you really don't need to encode amplitude and phase of a wave function for simpler calculations. It just turns out that, okay, yeah, I mean, you can say that sines and cosines arise naturally. because you need the norm of the complex vector to be 1. Okay. So since you need that to be 1, and so basically here if we see, let's say, um, where did I write the general matrix? Okay, I think even before this, yeah. Hmm. So yeah, if you see here, r1 square plus r2 square equal to 1. Okay. And from here it arises naturally because, sine squared plus cos squared is 1. So you can think of it like that. Yeah, like what you are saying is sort of correct. And I think you are trying to refer to this only. What is the total dimension of Hilbert space? Okay, so here we are dealing with qubits. So our Hilbert space is C2. So HS is C2. And dimension is basically the number of elements in any of its spaces. So let's take some basis of C2, say ket 0, ket 1, or let's say um, ket up and ket down and something like that. So all these spaces sets have two elements. So my dimension of my Hilbert space is 2. Does that answer your question? And actually, what will be the dimension of the Hilbert space depends on your problem. For example, let's say if you had a cube trig, then you would have the Hilbert space to be C3. And then your dimension of the Hilbert space would be 3. And that is actually what happens for spin 1 system. So if you have spin 1 systems, so basically that means the spin quantum number S is 1. Then you have 3 possibilities of ns. You can have ns minus 1, 0, 1. So in this case, it is actually you have to deal with vectors in C3, and so the dimension will be 3. Is that okay? So global phase represents the same point in the block sphere. Is it possible to represent the local space in block sphere? Uh, yeah, so basically local phase, if there is different local phase, then they will correspond to different points. So okay, let's look at that also with the help of an example. Acha, so let's say we take the ket plus, okay? Ket plus lies here, right, on the x-axis. Now, so ket plus is, if you write, this is 0 plus 1 by root. Now, let us introduce a phase. So 0 plus e to the power I phi 1 by root. Okay. Then what will happen? So basically your theta will remain the same, as you can understand. Only your phi, which was 0, will now become some finite value. So let's say this is phi dashed. So phi will now become phi dashed. So instead of plus, you will have some other point in the xy plane. So which will be at an angle phi with ket plus. So if let's say we uh, say that this is some psi tilde. So psi tilde will be like this. Okay. So basically, whenever you would add an additional phase, then it will basically just rotate in the xy plane. So basically about the z-axis. Okay. Yeah, and that is actually something which we'll see next day. Yeah. There's some gates which rotates about the z-axis, but not by pi. They actually do something like this. Is that okay, Rajrupa? Okay, and Karthik is asking, maximum dimension limit exists for Hilbert space? No, it does not. Hilbert space can be infinite dimension. Okay. So yeah, there's no maximum dimension limit. So okay, basically, in conventionally, what you say, write in quantum, learn in quantum mechanics is about wave functions, psi x. Okay, and psi x actually belongs to a space of basically square integrable functions, which lies from minus infinity. So So basically, functions can also form space, vector spaces. So this is a vector space of some functions, and this is infinite dimensional vector space. So whenever you are writing, say, some wave function, not a wave vector, and now you might also ask, you, okay, how is this wave function related to a wave vector? So that is quite simple. It is just the projection of the wave vector along x. So does that sort of so this is basically the space of all square integrable functions. Integrable functions. So where the integration uh, where integration runs from minus infinity to plus infinity. Practically, I think it is limited by the. Yeah, yeah. See, look, qubits are not the only quantum systems. Okay, so if you are considering some system where you want to find this wave function psi x, basically, if you are trying to see that what is the uh, say probability of finding at different values of x. So for that, we would just take the wave function whole squared and take a graph over x. So in that case, the Hilbert space is not actually, and that is not a qubit situation. Remember, there are not discretized values of x which are available. There are infinite number of values of x which is available. So in such cases, so depending on the system that and also the degree of freedom that you are studying, that is also very important. For example, here we are only considering the spin degree of freedom of the cube. We are not considering the spatial degree of freedom, for example. So whenever you consider something like the spatial degree of freedom, then the Hilbert space will become infinite dimensional if all the space points are allowed in that sense. So it's not limited by the availability of qubits. Yeah, if you are only thinking about quantum computation, then yes. Yes, it is limited by the availability of how many qubits we'll have. That will limit. And we will see that if there are two qubits, then how we would describe the Hilbert space. That we will see next class after we are done with the general rotations. Is that okay? Okay, okay, okay. I think I forgot who it was. I think Anmol or somebody. Yeah, not Anmol. Aman. Aman brought up a very important point. You can actually describe like right matrices in different bases. For example, here we have in the 0, 1. So what he means by the 0, 1 basis is that when you write the elements of the matrix, it is like 1 by root 2 ket 0 ket 0 plus 1 by root 2 ket 0 ket 1 plus 1 by root 2 ket 1 ket 0 minus 1 by root 2 ket 1. But we could also write it in something like, say, instead of outer product of ket 0 ket 0, we could write something like ket plus ket or ket minus. So if you can also write, just like you can write vectors in different bases, you can also write matrices in different bases. Okay, so that is also an important point that is brought up, and I thought I would mention briefly. Okay, so any other questions? I would also encourage other people to also interact more. Yeah, some of you are interacting, giving answers, asking questions. So, like the rest of you can also try to interact more. That will actually might clear other people's doubts as well. So, all right, I would be here for 2, 3 more minutes, and then we'll call it a day. When is the next class? As usual, the schedule is dynamic, so I can't tell you right now, but okay, we will definitely let you by email as usual. Yeah, yeah, I will be covering projectors. Yes, actually, yeah, I will be projective operators. I think you mean. Yes, projectors and projective operators we will be covering because we will cover density matrices as well. So if you want to, so when we will go to density matrices, the probabilities and all are defined in terms of the projectors only. So we will have to cover projectors. Okay. So I think there are no more questions for today. I'll end the meeting now, and okay, see you. Bye.